The match made in heaven. Sodium again wants to lose its electron, chlorine really wants to gain an electron. So what they end up doing is literally sodium gives its electron to chlorine, right? It gives it. Now sodium has 8 electrons in its outer shell, chlorine will now have 8 electrons in its outer shell. Again, the outer shell for sodium will disappear because it only has one. You can't have an Earth's orbit without the planet, right? If the Earth disappears, the orbit disappears as well. Sodium is happy, chlorine is happy. This, by the way, is known as a dot and cross model. So you show how this reaction is taking place. And this particular part you're required to draw in the exam. What is forgiving in the exam is that you only get to draw the outermost shells. That's what you have to draw. Okay? You don't have to draw everything inside, so it gets very easy. And that's it. But again, let's focus on the math. Look how convenient this is. Sodium really wants to lose its electron. Chlorine really wants to gain that electron. And they do that. Chlorine has a negative charge right now, and sodium has a positive charge right now. Now, chlorine has a negative charge on it. Sodium has a positive charge on it. What's going to happen between them? Now, if you remember from physics or static electricity, if you have a negatively charged comb, when you brush your hair with it, and your hair has a positive charge, there's attraction between them. These charges, if they have these opposite charges, they attract. Why does the electron rush towards the proton, right? Why does it stay in orbit? Because the proton is attracting it, right? And because this has a net positive charge, and this has a net negative charge, they're attracting each other now. So they'll line up each other, like line up next to each other, kind of like this, without the brackets. The brackets, we added them, but they'll just line up like this next to each other. But the story kind of really doesn't end there, because you never have just one sodium atom and one chlorine atom. You have millions of these, even in the smallest of grains of sodium chloride. So what's going to happen is this side of the ion stays negative, this side stays positive. So another sodium ion that's donated its ion electron will sit right next to it. So it's going to be sodium, chlorine, then sodium. Then over here, a chlorine will sit next to the sodium. And this will keep on repeating. Okay? And it'll keep on going until forever. But it still doesn't stop there. They'll also start piling up on top of each other and forward and behind of each other. Let's see that a bit clearly in the next diagram. This diagram over here, we've omitted the sodiums and the chlorine title and color coded it so it looks neater. Okay. So the positive, the plus ones are all the sodiums, and the minus one are all the chlorines. Now try to ignore everything that's in the background, and let's look at the first layer, all of this particular square right in front. Okay? How do we look at the sodium? This sodium, I know it's sodium because it has a positive charge, has 4 chlorine atoms around it, and each chlorine atom has 4 sodium ions. I misspoke earlier. Ions around them, right? But they're not really 6 if you think about it, because this is just a corner view, right? This sodium is right in the corner. So there's also a chlorine right behind it, and there's also a chlorine right in front of it if this were to continue. It's not continuing, but if it were to continue, there would be one in front. So each chlorine atom is surrounded by 6 sodium ions, and each sodium ion is surrounded by 6 chlorine ions, and all of it balances out, and they're held together very tightly because of this attraction. Okay? They're held together strongly in place, this attraction. Now this attraction has a name. This attraction is called the ionic bond. The ionic bond. This is what an ionic bond is. When an atom like sodium gives its electron to chlorine, between them there's a strong attraction that keeps them together in place. That strong attraction is an ionic bond. Okay? Very simple. Okay? And to show this chemically, this is how we write it down. So sodium will react with chlorine. Chlorine normally is naturally as Cl2, and they combine to form NaCl. So we have two chlorines here, so let's just, I think we'll have to balance it like this for now. Okay, two sodiums require two chlorines to form NaCl. And note over here it says NaCl. That doesn't mean it's one sodium atom bonded to one chlorine atom. It looks like that, definitely. That's what a lot of people get confused by as well. But you can never have one ion or one atom of sodium bonded to another ion or atom of chlorine, because everywhere else it still has that charge. It'll attract more things and they'll make this huge, this is just a tiny cube. This goes on, this pattern repeats on for like millions of these ions. It's huge, yet so tiny because these atoms are tiny. So in a small grain of salt, because sodium chloride is salt, you have these repeating patterns in the entirety of the salt. Okay, and that's what just table salt is. Sodiums and chlorines held together tightly in that lattice. Okay. Now, what does Na and Cl mean over here written like this? They're just complementing on the ratio of these ions. For each sodium ion present over here, there's also one chlorine ion. And if you do the math, it will balance out. And why am I so confident in saying that is, if you had more sodium and more chlorine than chlorine, if you had more sodium than chlorine, this entire thing would have a net positive charge. And that wouldn't go too well with the laws of physics, right? They would become very reactive and something weird would happen until and unless the sodium and chlorine charges are balanced out. And the only way to balance them out is when they're in equal ratios. So another way of looking at this particular chemical formula is, for each sodium there's one chlorine. Okay, but you almost never, you never, why am I saying almost, you never write 1 here when you're implying 1. For any other number you write that number down, but you never write 1 in these equations, right? Okay, let's move on now. Now this repeating pattern of the solid structure is known as a lattice, and this lattice grows to form a giant three-dimensional structure, meaning that ions are on top of a particular ion, below it, left and right, forward and backward, all around it, right? It's called giant because it contains a very large number of ions. Even a grain of salt is just repeating patterns of repeating ions, positive, negative, positive, negative. So it's a giant structure, and the compound for, in our example, is sodium chloride or just common salt. For some better understanding, let's try drawing this particular lattice, and I encourage you to draw it with me. So here's a positive charged sodium ion, and it's surrounded by 6 chlorine ions, right? But because this is my edge, this is my corner, I won't draw 6. And I'm not really drawing the forward and the backward one. I'll just draw the ones on the side and the top and bottom. Well, not really the top in this case. The one at the bottom for this is over here, and the one on the right is like that. And I'll just continue this pattern. So sodium is over here. Sodium is also over here, right? After each ion, the next one is different. So chlorine is over here, chlorine is over here, and sodium is over here. Okay. And just showing these attractive forces by drawing lines between them, kind of like this. I don't like that particular line. And we're done. Okay. Now what you want to do is probably show one more side of this, right? So let's draw the pattern immediately behind it, and that's easily done. We'll just put, so I want to draw the ion bonded to this sodium at the back. So what's going to be bonded to this is going to be chlorine. So I'll just put that here, and there won't be a chlorine over here. I'll just skip this, and I'll identify all the places where chlorines are. Kind of like that, kind of like that. Okay, kind of like, okay, that's in the wrong place. I'm using this as my guide for the placement, right? And if I can still draw, kind of like that. Not here, and kind of like that. Okay, let's draw all the sodiums now. Like that, and like that, and like that. Okay. And now time to join them. Let's join them like this. A bit neater. Like so. Okay. Really confusing so far. I think you're confused, so make sure you practice. Now what I want to draw is draw lines like this, because that's how I arrange them, right? And I'll try to match all of them together. I'll try my best to keep, my trick is to make a neat diagram is, I try my best to keep my angle consistent, right? So it's going to be like this, not like, it's not going to go vertically, or don't have too much tilt to it. Okay, keep it consistent. And I make one here, 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 one here. And I think it looks much better with the lines in the middle. So you can see it's a cuboid sort of structure, and they're all repeating. Okay?